So we are going to go over today over some basics of magnetostatics and electrodynamics that are very important for considering in spintronics and magnetic phenomena in spintronics. So, for example, I have here this. We have two here wires, and we have two directions of the currents. And for first case, we have currents parallel to each other, and in the first case we have, in the second case we have currents opposite in direction. In the first case, we will have magnetic field created by each of these wires on the other wires, and they will create these magnetic forces. So, for example, let's see how this force is created. Here we have current on the left wire that's directed upward, and it creates magnetic field using right hand rule. It will be in this direction. And on the second wire we will have current that will be parallel to this direction. And we will have here that the magnetic force will be just attracting. So it is because if you consider here some current created by the positive charges, and they have velocity v parallel to the E current. In this case, we have Lorentz force that's equal to Q, V, and the vector multiplication of V and B. So vector multiplication of V and B creates this vector direction of force that will be attractive in this case. So basically, for this case, when we have current that are directed parallel to each other, we will have force that attracts each other. So this force, we can find out that it's equal to this magnetic force, Q times V times B, and this is Lorentz force. Now, if we consider some motion of the charge, Q charge, small q charge, in B magnetic field, and we can see that it will be directed, its trajectory will be either circle or on spiral. So let's consider if it's on spiral trajectory. In this case, we can equate this force, magnetic force, to the centripetal force, and which is equal to mv squared divided by r. And in this way, we can find out the momentum that will be equal to Q times P times r. And P here is the momentum that's equal to multiplication of mass and velocity. So in the case, if we have speed of this charge not perpendicular, velocity not perpendicular to magnetic field, in this case we have to pick up perpendicular projection of the magnetic field, of the velocity, and equated this force QV times B to the centripetal force. And this way we can find out radius of the this circle motion. But in this case, we will have motion on spiral because of the vertical projection of the velocity speed here. So after all, the trajectory will look like on the spiral here. Now, if we take electromagnetic field, this is the electromagnetic field, we have magnetic field and electric field. So magnetic field is directed on the x-axis, and electric field directed on the z-axis. If we have Q charge at t equals to 0 at point 0 here, and we need to find out here trajectory. So now we have to consider here the magnetic force and the electric force. And after all, this trajectory will look like this. So it doesn't look like in previous case. So if we consider here the creation of the current, it's created by the charge Q that will be flowing in some wires. So in this case, we have formula for the current that equal to dq dt. In this case, dq is the amount, differential amount of the elementary amount of charge that goes through some cross section in the wire, and dt is the time during which this dq charge flows through some cross section. So if we look here to the magnetic force, and we can find out that in the current we will have many charges that will have, for example, dq charge, and we can sum all these forces, magnetic forces that's acting on the dq charges, and this force will be equal to the integral of these magnetic forces, load of magnetic forces. So here dq in the case of flowing through the wires, we can write down as lambda times dl, where lambda is a linear charge density, and the lambda goes to the v, and the lambda times v in this case will equal to the current E. And we finally will have this force that will look like that it's called ampere force. So now ampere force is a force that's acting on some length of the current that we will have in the wire. Now this amount of the current that we found out that equals to the linear charge times V is found out from this line here. So E times E equals to dq dt. dq is the lambda dl, and dl dt just gives us the speed of the charge, and this way we find out that E equals to lambda times V. Now this is the alternative formula for the ampere force. In this case we can write down E integral dl times V. In this case, current E should be has to be constant on throughout all the length of the wire. So let us consider this usage of these forces for this problem. So we have here some wire, wire. In this case, it's just we'll have this rectangular form, and we have current flowing through it, and it is entering magnetic field that it is directed inside of this screen. So the direction is shown with this B magnetic field. So in this case, we have magnetic field acting on all the elements of this square loop, and the length of this loop on each side will equal to A. We have to find out the amount of current that it needs to be flowing through this rectangular wire, so that this weight of mass M will be equal to it. So magnetic force should be equal to this M force, weight force that exerted by this load. So in this case, we have current E on the upper side of this side, and it creates F1 force that's acting upward. Its value equals to E times B times A, and force, weight force is equal to M times G. We equate two forces, F1 and F2, and from this equation we can find out this current that's equal to mg times divided by B times A. Now this force, the current should be larger than this current in order for this rectangle, for this square loop not to leave this magnetic field. And if this magnetic field, this current is smaller than this current, in this case weight of this M force will be larger, and this square loop just goes down. So we have three kinds of the currents. We can have volume current. First we can have volume current, and this volume current is described on this slide here. So we have here this some kind of this volumetric current, and it flows through this wire that has ds cross section here, ds cross section. Now, in this case, current can be described by current density, which we can accept as a J, which is equal to di divided by ds cross section. And for di, we have dq divided by dt, and dq is equal here rho times d tau. So rho here is the density, charge density of this volume charge. And we find out that from this expression that it equals to rho times v. And finally, this density, current density is equal to current charge density times v speed of this current. Now we can use this formula for to solve this problem. So, for example, we have here a wire that has cross section with radius of a, and the total current is equal to I. Now we are going to find out this density, volumetric current density. So according to that formula that we used before, it should equal to E divided by P A squared. Now in the B part of this formula of this problem, we have formula for the density current that is equal to K times R. In this case, we need to find out total current. So total current is equal to G ds, and we find substitute here for J K times R, and ds is here in polar coordinates is equal to R dr dphi. So here we have K, it's just constant, and here we have two integrals. One is R squared dr, and second is dphi. So the integral for dphi gives us value of d2 pi, and the integral r dr gives us a squared r squared dr gives a cubed divided by c, and finally total current is equal to 2 pi k a cubed divided by c.